Continuing our discussion of isobaric work from the last slide in the first part, another way to express this is shown in this graph. What you have is the pressure, which remains the same because of the isobaric nature of the work, graphed against the volume, and the volume changes in this regard. And what you can see here is this area under the curve represents the P delta V, or the work that's performed. So a graph that shows this, pressure versus volume, is a way of showing the work that's done, and the area in this area right here is the representation of the work. Now if you do the similar diagram, but now you notice that this is not isobaric. The pressure is changing as well as the volume changing, and what you end up with is an estimation of the work using several small boxes to represent small isobaric changes, each of which approximates the amount of work done. And the area of each of these boxes, if you add them all up, is an estimation of the work done. And if you're able to calculate this right here along this path without using the estimate boxes, this area under here is the work that's performed. Now if you're traveling in this direction, the pressure is going down while the volume is going up. You're still performing work. If you reverse the direction, it just reverses the sign of the work that's done. So this total area under the curve is a work output. Conversely, if you're heading in this direction where the volume is decreasing and the pressure is increasing, so it's work being done on the system instead of by the system, it's essentially work input, which is the same as a negative work output with the same path. So, work done going from A to C can be done in this direction along an isobaric line, and then down the pressure line this way, or it can be done going in this direction first, followed by this direction. If you go path A, B, C, the work is greater for path A, B, C than path A, D, C. You can see that the area under the curve here is greater than the area under the curve here. And this is because the former is performed at a higher pressure than the latter. So if we look at part B here, and we look at it in terms of either direction, if this represents the pressure on this line and this represents the pressure on this line, you can see that the total work done in a cyclical process, that is, if you start at A and go to B, then to C, then to D, then to A, so if you do this cycle, is the area inside the loop. And this down here subtracts out, so it is just the area inside this triangle. See here, the work done in a cyclical process such as this represents the area inside this circle. And since it will be a positive, or work done by the system on the outside environment, if it's traveling in a clockwise direction. However, if it's traveling in a counterclockwise direction, it will be negative, and it'll be work done on the system by the surroundings. So up here, if you're traveling in this direction, it's work done by the system on the surroundings. If you travel in the opposite direction, it's work done by the surroundings on the system. And the same is true here. Now there's another term here. There are two terms here, I'm sorry. The first term is isothermal. Isothermal process is a process in which there's no change in temperature. adiabatic process is a process where there's no change in heat. And so you have the pressure again and the volume on this. If you perform this first part from A to B with no change in temperature, now there has to be a change in heat for this to occur, then this is called isothermal expansion. On the other hand, if you drop down on this line, then you have no heat exchange. Temperatures do change, but no heat exchange. So from A to C is called an adiabatic expansion. Both of these are expansions because the volume is increasing. Both start at A, but the isothermal process does more work than the adiabatic process because heat transfer into the gas takes place to keep the temperature constant. So the reason that this line is above this line is that heat transfer has to occur in order to keep the temperature the same. So with that heat transfer comes a higher pressure along the isothermal path than the adiabatic path, and because it's a higher pressure, you have a greater amount of work. The adiabatic path ends up with a lower pressure and temperature at point C, even though the final volume is the same as it is for the isothermal process. So the cycle A, B, C, A produces a net work output. Obviously, if you go in the opposite direction, you have to do a net work input. So let's do a couple problems related to this application of the first law. Steam is used to drive an old-fashioned steam engine, and is supplied at a pressure of 1.75 times 10 to the 6 pascals to a piston whose radius is 0.2 of a meter. And if the piston moves 0.8 of a meter, how much work is done? So let's go to our notepad here. And so the work is going to be equal to P delta V, which is equal to P times the area times the distance that it travels, which is equal to P times pi r squared, that's the area, times D. And so this is going to be 1.75 times 10 to the 6th, and that's newtons per square meter, or pascals, times pi times 0.2 squared times 0.8. And if we do all this mathematical calculation here, we get 1.76 times 10 to the 5th joules. Now the second part here, a hand-driven pump, tire pump, has a piston with a 2.5 centimeter diameter and a maximum stroke of 30 centimeters. How much work do you do in one stroke if the average pump gauge pressure is 2.4 times 10 to the 5th pascals? So again, the work is going to be P delta V, which is going to be PAD, which will be, now we've got 2.4 times 10 to the 5th times, and pi times 1.25, this is half of the diameter, times 10 to the minus 2 meters squared times 0.3. And if you do the math here, you get 35.3 joules of work on that one. the next part says, what is the average force exerted on the piston, neglecting gravity, etc.? Well, work is equal to force times distance. So force is going to equal work divided by distance. And the work we just calculated was 35.3 divided by, and the distance was 0.300. So the total force is 118 newtons. Okay, let's move on to the second law of thermodynamics. And the second law of thermodynamics has to do with the transfer of energy, etc. So what we have here is what is known as a one-way process. So for example, if you have a vacuum and the vacuum is released, it's a one-time puff, and then it's irreversible. First of all, A is the first example. Heat transfer occurs spontaneously from hot to cold. It never occurs the other way around, where if you put a warm object, it never separates into two objects, one of which is hot and one of which is cold. The second one here is if you are traveling and you convert kinetic energy into thermal energy by putting on the brakes, you cannot go the other way around. That is, take heat energy from the brakes and convert that into kinetic energy. And then this third one is if the gas is let into this vacuum chamber, it expands and fills the chamber. Once that occurs, it will not spontaneously recollect into a vacuum. So all of these are examples of spontaneous processes. So here we have one of these. Here we have a high temperature and a low temperature situation. In this situation, heat transfer occurs spontaneously from high to low, and it's consistent with the second law of thermodynamics. In this heat engine situation, we have heat transferring, but remember, with a heat engine, we're converting some of this heat into work. And we end up with the heat from the hot side and the heat from the cold side and the cold temperature. The work done is equal to the hot side minus the cold side is the work that's performed. So if you have the transfer of heat from a hot to a cold reservoir and work is performed in the process, again, this is an irreversible situation because you cannot reverse this and take it back. So here's an example. It looks very much like a car. This is the way a car piston works. So in a car piston situation, it is impossible for any system of heat transfer to completely convert to work in a cyclical process in which the system returns to its original state. In other words, you cannot possibly, in this cyclical state, convert all of the heat that's generated in this process into work when it's returned to its original state. There will always be heat lost, and that's the way the second law of thermodynamics works. The usable energy is always less than the total energy available. So here's a diagram looking at this process, and we have the high level of heat at this side, the low level on this side. And basically what occurs is you have heat, the transfer of energy with the heat remaining the same in these two situations, but at the same time work is done because there's a change in volume. Okay? And so what this shows is if you take this situation, the area in here represents the work that's performed. You have a high level and a low level, and there during two of these parts of the cycle, there's no heat transfer. Now, an important formula to remember is the efficiency of these sorts of engines. And these sorts of heat engines, the efficiency of the heat engine is equal to 1 minus the quotient of the amount of heat in the cold side divided by the amount of heat on the hot side. So let's look at some problems related to the second law of thermodynamics.